All right, this is lesson 7.2, exponential functions. We are working in unit 14 on Khan Academy, exponential growth and decay. After this lesson, you'll be able to do skills 5, 6, and 8 from that unit. Our objective is that you'll be able to identify and graph exponential growth and decay functions. So, basically, if the variable is not in the exponent, then it is not an exponential function. Here is an exponential function. We have y, or you could say f of x, equals some number a times another number r raised to the power of x. Again, x, our independent variable, is the exponent, and that's what makes it exponential. This a here is going to be a number. Notice that a has to be non-zero. That's going to be our initial value, our starting point. Graphically, that means it's the y-intercept. And it should make sense why this is the y-intercept, because the y-intercept has an x-coordinate of 0, right? If x was 0, we'd have r, some number r, raised to the power of 0, which you should remember from last chapter. Anything to the 0 power is 1. And so we really just have 1 times a, which is just going to be a, and that's going to be our y-intercept. The other letter here, r, that represents a number, is going to be called our growth factor or our decay factor, and I'll tell you how to determine if it's growth or decay later in this lesson. I use the letter r, though, because it stands for ratio. You should be thinking of the geometric sequences that we learned about in the last lesson, because it's that same kind of ratio. We're multiplying by the same number every time as long as your x values are evenly spaced, right? Again, there are some stipulations. For the purposes of Math 1, r is going to be positive and r is not going to be 1. To explain why a can't be 0 and r can't be 1, really they could, but it would be what we call a degenerate form of an exponential function. It's not truly exponential. If a was 0, then y would be 0 times a number. Whatever number that is just going to be 0, right? So if we allowed a to be 0, we would just have the line y equals 0, which isn't really exponential, not truly. It's a degenerate case. Same thing for when r is 1. We don't want that either, because our function would then become some number times 1 to a power. No matter how many times we multiply a by 1, it's still going to be 1. So again, we would just have a horizontal line. So just so that we have an interesting exponential curve, I'm throwing these on as well. We're not going to have a be 0. We're not going to have r be 1. All right. Identify the following, if the following are exponential, and if they are, what's the initial value, that's a, and what's the growth or decay factor, that's r. Sorry, I have a small typo. Some textbooks use the letter b, which makes sense, b for base. I like to use r to make that connection between geometric sequences and exponential functions. So if you could please just change those b's to r's, and then we'll move on. All right. Let's take a look at this first function here. Is it exponential? Well, the exponent x is in the exponent, or the variable x is in the exponent, so yes. This is a little tricky though. I'm going to zoom in, because all we have is 2 to the x power. There's nothing really written in place of a, but that means it's 1 times 2 to the x power. So our a value is not 0, it's 1. And our growth factor is 2. It's that base that's raised to the power of x. All right, let's try the next one. Is it exponential? Well, is the variable in the exponent? No, it's not. The variable is not in the exponent. So we don't even need to talk about our a and r values, because this isn't an exponential function. All right, I want you to try the remaining 3 on your own and then come back and check your work. Okay, hopefully you found that the first 2 functions are exponential, but the last one is not. And I want to explain why the last one isn't before we go to the first 2 again. In this last function, the exponent is e. And you have to remember that e, in math, e is a constant. It's a number. Remember how pi is also a constant? It's about 3.14 blah, blah, blah. E is the same way. You see e in a lot of exponential stuff. You'll learn more about it probably in math 2 or 3. But it is a constant. It's about 2.7. So this is not an exponential function. X is not in the exponent. Okay, but for the other 2, we can see that our initial value, our a value, is -3 here, and in the other function it's 10. This is a good point to notice that, yes, a technically could be negative. You could have a -3 there, but for the purposes of our class and all the stuff you'll see in Khan Academy and on our quiz and everything, we're just going to deal with positive values of a for this class. You should know that it is possible to have negative a values too, and you'll see those in future math classes. All right, and then our r values, for this function, x is the exponent, so the base, 2.6, that's our r value. The other one's a little bit tricky because our exponent isn't just x. If we rewrite this using our negative exponent rule that we learned in chapter 6, this is the same as 10 times a sixth to the power of x. And now x is the only thing in the exponent. So our common ratio, or rather our decay factor is what we're calling it now, would be 1/6. Okay. We're going to quickly compare linear graphs and exponential graphs. So I already did this one because we spent basically all of last semester graphing lines. This is a line, it's in slope-intercept form, so I graph this line because I know that my y-intercept is 3. My slope is 2, so I went up 2 and over 1, and I put another point. And if you need help graphing lines, feel free to go back to chapter 2. I've got all my videos posted. However, you should also know that if all else fails, we could make a table, right? So we could have done a table of input and output values and done the same thing. Plugged in our function and got some outputs. But I'm not going to do that right now. I will do it for the next graph. So exponential functions should be relatively new to you. Let's make a table. So I've got a column for my inputs, my x values, and a column for my outputs, f of x, or y. And again, our initial value is this a value here. That's going to be a nice one we should always try to start with. Our y-intercept, our starting point, is 3. Now from there, we're multiplying by 2 every single time. So we could just plot the terms in that geometric sequence, right? We could say that when x is 1, I'm just going to double 3. This is going to be 3 times 2, which is 6. Or if you'd rather, you could use our function notation f of 1 is 3 times 2 to the power of 1. 2 to the power of 1 is just 2. 3 times 2 is 6. And we could go from there. When x is 2, f of 2, the y value, would be 3 times 2 to the second power. Plug in 2 for x. 2 times 2 is 4, and 3 times 4 is 12. And you could even do, here, let me put that in the table before I forget. We could plug in negative values now. When f is -1, we'll have 3 times 2 to the power of -1. But that's 3 times a half to the power of 1, which is 3 halves, or 1.5. 1.5, 3 halves, however you want to write it. And let's go ahead and plot those points now. When x is 1, y is 6. When x is 2, y is 12, so 6, 7, 8, 9, 10, 11, 12 would be like 1 square off of our graph, somewhere there. And when x is -1, we have 1.5. And hopefully you notice that the y value is 3 here, and then it's half of that here. It's 3 halves, or 1.5. And we can cut that in half again and again and again. And we'll end up getting points that look something like this. I'm just approximating, but my y value is getting cut in half every time. No matter how many times I cut 3 in half, get 1.5 or 0.75 or whatever the next one is, I'm always going to have a very small but positive number. It'll never become negative. It'll never cross, this graph will never cross the x-axis, because those y values are going to stay small but positive. So let's just highlight that for now, because that's interesting. We'll talk more about that on the next page, but it seems like our graph, as we move further to the left, it's getting close to this line, but it's never actually going to touch it. It's never going to cross the x-axis. Okay, so right here I have some rules on how to tell if it's growth or decay. We do probably want to note that our function needs to look like that, and a and r need to be positive. As long as a and r are positive, we have exponential growth when r is bigger than 1. And we have exponential decay when r is less than 1. So, oops, I forgot to cover this, but that's okay. Go ahead and fill in the blank. We'll have growth when r is bigger than 1, just like we said. And the graph will grow away from this vocabulary word asymptote as you move from left to right. So go ahead and put asymptote here. That's that highlighted part that I marked on the last graph. It's a line that the graph will approach but not touch. All right, so we've got the function 2 times a half, or 2 times 1.5 to the power of x. Notice that our r value is bigger than 1, so this is growth. Let's plug in some points. When x is 0, our y-intercept is going to be this 2. So we've got the point right here on the graph. And let's just plug in a few more above and below, or rather to the left and to the right of it. When x is 1, we'll have f of 1 is 2 times 1.5 to the power of 1, which will end up being 3. In fact, let's put it here. And f of 2, I can plug in 2 for x. And 1.5 squared, if I take that value and multiply it by 2, I should get 4.5. You can check my math. We can go the other way as well. F of -1, we should end up getting 2 to the 1.5 to the -1 power. Again, that should end up being 1.33. I'm rounding. I should probably squiggle. There we go. And if you plug in -2, our output should end up being about 0.89. Again, that's from plugging in -2, so that'll be 2 times 1.5 to the power of -2. And if you want, you can write 1.5 as a fraction, use that negative exponent rule. We can totally do this by hand without a calculator, but for the sake of time, I'm just going to move on to the graph. All right, so when x is 1, y is 3. And when x is 2, y is 4.5. When x is -1, we have 1 1/3-ish. When x is -2, we've got 0.89, so a little bit under 1. These almost look like they line up. They don't, but if you were to pick another point, like let's say when x is 3, we should end up getting 6.75 as our output. And so that would end up being 1, 2, 3, 4, 5, 6, almost 7, somewhere about here. You can see it does actually start to curve. So again, it'd be really close to the x-axis on the left side, and as you move to the right, it'll jump away from that asymptote. There's the asymptote. All right, try to graph this one on your own. We have 1/3 times 2 to the power of x, and then come back and check your work. If you made a table first, you should have got something like this. I showed my work here for you for some of them. You can do that for every single input if you'd like. The graph should end up looking like this. Again, it's growing away from the asymptote as we move from left to right. So these are both growth functions. All right, so hopefully you notice that there are some easy points that you should pick when you're graphing. The first one is always that starting point, that y-intercept. And then when it's growth, it's nice to plug in 1. Notice in this first one here, we had a nice whole number output. The only reason we didn't have a whole number output here is because this example had a fraction for a. But if a was an integer, this would have also been an integer because we're just multiplying by 2. So we have our 2 nice points we want to pick when we're graphing growth. And again, there's just a note that we'll have an asymptote on the x-axis. All right. Let's move on to decay. That's when the factor, the ratio, is less than 1. It's still positive. That's why I have the 0 is less than r here, but it's less than 1. So it'll actually decrease towards the asymptote as we move from left to right. What this is saying here is that growth looked like this. Decay is going to look more like this. It's going to still approach the asymptote, but on the right side. So we have a function here. Hopefully you notice that our ratio is 1/2, which is less than 1. So this should be exponential decay. Let's graph it together. Let's see what happens when x is 0. That's going to be our starting point, right? Our a value, 3. Let's try a few points to either side. So when x is 1, we'll have 3 times 1/2 to the power of 1, which is just 3 times 1/2, which is 3/2. Or 1.5 if you want to think of it that way. When x is 2, I could plug in 2. That'd be 3 times 1/2 to the power of 2, half squared, which is 1/4. So we should end up getting 3/4, which is 0.75. This isn't looking nicer. I think if we plug in 3 or 4, we'll actually get uglier decimals. But let's go the other way. When x is -1, I can find out what f of -1 is. It would be 3 times 1/2 to the power of -1. But according to my negative exponent rule that we learned in chapter 6, that's the same as 3 times 2 to the power of 1, which is just 3 times 2, which would be 6. And then I'm not going to show my work for it. You can check it on your own if you'd like. But if I plug in -2, I should end up with 12 as my output. So we can graph this. We have a point here. That's our a value. And as we go to the right, we're getting cut in half. And then as we go to the left, it's actually growing, getting taller. So when x is -1, it'd be up here. And when x is -2, this seems like the mirror image of something we graphed already, I think. But it does show decay as we move from left to right. It's getting really, really close to this asymptote. Because again, we're just going to take 0.75 and cut it in half, and cut it in half again, cut it in half again. It'll always be positive, but it won't, it'll keep shrinking closer and closer to 0. Okay, now for the sake of time, I'm going to cut this one. I did have room for another graph, but I think this is enough to show you the difference between growth and decay. Last part, this should say decay, so please fix that typo. There are 2 points that will be nice to graph. Again, that starting point will always be nice to graph. We want that 0, a. But hopefully you noticed that when we plugged in 1, the exponent ended up being like, well, we ended up getting like 1/2 to the power of 1. We got a fraction. So we don't actually want to deal with that. But notice when we use that negative exponent rule, we ended up getting a nice whole number here. So that's why when it's decay, the second point you really want to use is when x is -1, because you use the negative exponent property. Excuse me. That's it for 7.2. As always, ask a question at the end of the video, and I'll see you all in the next one.